Hi and welcome back to the Autoware course. My name is Florian, I'm a co-founder of TERNARIS and I'm going to show you the MARV Analytics Retrieval and Visualization platform. MARV finds back files from ROS1 and ROS2 on a scan route on your hard disk and visualizes them in a web interface. There is an API, you can interact with it, and you can extend it with your own algorithms. Apart from ROS1 and ROS2 back files, you can extend it to any other format as well. MARV exists in 3 flavors. There is an Enterprise Edition, there's MARV Automotive, which we're doing in cooperation with Apex AI, and there is the Community Edition, which is free and open source and focus of this tutorial. In order to follow this tutorial, there are a couple of prerequisites. You're going to need Docker, you need Git, Git LFS, rsync, the repository with the tutorial code and this README org file, and a checkout of the MARV Robotics repository from the Community Edition. And if you're planning to do all this later, like to follow the sessions on a low bandwidth network, you should run git LFS pull on the scan route first, and also Docker build. The Docker build will be needed in session 5. It's a custom Docker container, and git LFS pull on the scan route will give you the example bag files we selected. That's it. Once you're installed, like if you fetch these things, you're gonna have a directory looking something like that. The MARV Robotics checkout is in the tutorials repository. So we cloned it into that repository next to the side folders. And those side folders are corresponding to the sessions. Let's start with the first session. In this first session, we're going to install the MARV Community Edition and use its default configuration to set up a site and interact with it and see a little bit what it does. Let's start with the installation. In the prerequisites in the intro, I showed you that we need a MARV Robotics checkout, and now we are going to explain that MARV Robotics checkout, that we want the TERNARIS MARV Robotics image. That's the official Docker image for the MARV Community Edition, and we want to use that as default image. Once we have done that, we can set up a site. It's site 1 for the first session. We copy from MARV Robotics the example configuration into that site, and after we've done that, we are good to go to start the container. Run container on site 1 with the scan route. In that scan route, I will see in a moment, MARV is starting up. That looks great. MARV is running. Let's have a look over here. MARV is running and we need to sign in to do something. But you can access, for example, the documentation already, which is contained with the MARV installation. Now, having started MARV, our site folder got some additional files. There's a database directory in which MARV stores all its information it has about the back files, as well as tags or comments you're adding. There's the config file, we copied from the default site contained in the Community Edition. There's a session key. If you delete this one, then users will have to relog in. And there is a store directory in which MARV is running nodes that extract information from back files, and this is being stored in the store. If you have many back files, it will be also difficult to recreate that or time-consuming to recreate that. So it's less valuable than the database directory, because in theory you can recreate all information in there, but it might not be feasible in praxis. In order to continue, we need to create a user. For that, we need to enter the container, and we are starting the container in the background. We're detaching it. The detach parameter is directly passed to Docker. So if you want to pass the Docker container any other arguments, that's the place to put it. As the startup can take a moment, it's good to check whether it's really running. Or what is the state? It is running. And now we can enter this container. Inside of the container, everything is configured that MARV knows to operate on its site, so you can just stay in the home directory. We're doing a MARV user add demo. And after we added that user, we want him to be also in the admin group, so he has some more powers. Once we have done that, we can log in with that user. So far there is no data sets. Let's run the scanner. The scanner found some data sets. When we are reloading the web interface now, you can see we have a couple of data sets from the Kitty raw data set, which we trimmed down a little bit for the purpose of this tutorial. And we have a ROS2 recorded in the simulate in the parking lot as part of one of the other lectures. Let's start some nodes, or basically all configured nodes. We will see later how this is done, but for the moment we just run them on the bags collection. You can have multiple collections. We'll not go into more detail here, it's in the documentation. But for this bags collection, we are now running nodes, and we'll see while these nodes are running that step-by-step information will show up here. The first bag is being processed. And now for the first Kitty bag, we have a start time, we have the end time, and duration. So this is a listing view of all your data sets. In addition, there is a summary view up here, and that summarizes information of the currently displayed bags. We also have filters, where we can filter for specific types. And we can add tags. So we select, for example, here 2 tags. We give that a label. Those 2 are labeled. We take 2 more. And now we can filter for tags. We want either bar or foo, any of these. Apply. And we see now all bags that are tagged either bar or foo. Further, we can look into more detail at one bag. So the ROS2, meanwhile all of the processing has finished. So let's take a look at the ROS2 file recorded from the parking lot. There is connection information, the topics contained in this bag. There is position and orientation. You can see how the car was moving, in which direction, the northing and easting, as well as the changes of the height of the car, or the altitude of the car. And further there is a trajectory. And this is loading a map in the background. I'm on a bit slow network at the moment. Let's take a look at this in full screen also. We can switch here to a satellite view. You can see the parking lot where the car was moving around. Let's take a look at one of the Kitty bags, whether there's something else visible. Here we have in addition an images section, which is more like a proof of concept. It's like taking 50 equidistantly spread images from an image stream. And there is a video section displaying a video rendered from the image stream. Additionally, we can add comments. So, for example, Alice should take a look at this comment. And then we can go to the comments filter and look for all comments that contain Alice. And we find the one bag. I can also remove the other filter. There should still be only one. That's it. That was the first session. Thank you very much, and see you in a moment in the second session. In the second session, we are going to write a custom scanner. The motivation for this is MARV's default scanner finds bag files anywhere in the scan route, and it understands the concept of ROS1 ROS record split bags and groups them together into individual datasets. So instead of having each bag as one dataset in the listing, they will be grouped together. However, for our case now, we have other files there. We have some metadata information. We know for the kitty bags the category where they were driving. So this was in the city. We have a driver, which was Alice. We have an issue that is tracking that test drive, and we have the vehicle name from the vehicle being used for the test drive. And we want that information to be available to MARV for filtering and to display in the listing. Also, there is an XML file provided by Kitty labeling objects, and we want to use that to just count the amount of objects and display that in the listing. In order to do this, we're going to implement a custom scanner. A scanner is just a function that is called for every directory found in the file system, in the scan route. The second parameter is a list of directories contained within that directory, like the names of directories within the directory. And file names is the files contained in the directory. If there is no dataset YAML in the file names, we're not interested in returning an empty dataset. Otherwise, we reset the list of directory names to the empty list, so that instructing by that the framework not to recurse further into the subdirectories. And we create one dataset named after the directory, and all files contained within the directory will belong to that dataset. MARV expects here a list of datasets. In order to use that scanner, we need to define it in the configuration. We have a collection bags, and its first key is the scanner. After having defined that, we can scan for them. Now, throughout the sessions, we want to keep one site directory, so we don't have to rescan and create a user every time. And we have for every session a corresponding one, and we synchronize that onto the site folder we want to use. So site 2 is the one we're starting with, and we're syncing that onto site. Once we have done that, we can start MARV and take care here to use the correct folder. MARV is being started in the background. And it is up and running. It's not sufficient to just click in the front end, we need to reload. The user doesn't exist anymore, and the session key was deleted anyway, so we need to relog in for that. We are entering the container now. We're adding the user again. We're scanning for files. Now let's log in. You see now we have differently. It's the same set of bags as before, but now found by our new custom scanner. Let's run also the nodes on them. As you see, the ROS2 file is not in here anymore because we didn't create a dataset YAML for it. And the configuration we're now using for these next couple of sessions is much smaller, therefore running the nodes was much quicker than before. The metadata information is extracted, and if we take a look at one of these, we see now there's the dataset YAML file, there's the bag file as before, and there's the tracklets label file. And we have the connection section as before. The other sections we disabled for the purpose here. that was the second session. Thank you very much for listening, and let's head over to session 3. In session 3, we want to do two things. For one, we want to count the number of cars and display it in the listing column and filter for that. And the other, we want to, from our dataset YAML file, we want to extract the driver name, the vehicle name, and the link to the issue tracking that, and use them also to display in the web front end. Let's start by the number of cars. You see we are in the site 3 now, the code directory. We're going to sync that in a moment also to site. Code, like Python packages that are in the code folder in your site directory will automatically be installed by MARV, by the container being set up. And within that package we have now one module, that's the metadata module, which defines two nodes. Let's take a look at the first node, the objects node. First, we want to use it to filter and for filter and listing. And the filter and listing is populated from the store. That is for performance reasons. Like we're extracting data from the back into the store, and afterwards we can use that to configure filters and listing without reopening the back file. And also for filter and listing, then that information enters MARV's database to have a performant filter and serving of the listing. As we want to use the objects node for filter and listing, we need to make it persistent, to be stored in a store, and for that it needs to have a type defined here as parameter to node. We take a look at that type definition in a moment. Then this node is using one input stream, which will be handed in as dataset, and which uses the MARV node dataset, which is the most basic node, as its input. MARV thinks in streams. The dataset stream is a stream with one message. And MARV nodes are generators that communicate with the framework by yielding requests, and the framework responding by sending in messages. So dataset is our first message here. And we're looking in the dataset files for the file that ends with tracklet labels. If there is no such file, we return we have been called on a dataset that is not of interest for us. You see we introduced the bug here, which we're going to see in a moment how we're going to debug that. And then we open that XML file. We use the element tree to find all nodes with the object type car, and we publish a dictionary with one key cars with the length of the cars list, so the count of the cars. Let's take a look at the schema. We're using Captain Proto to store node output in the store. It's a schema language and serialization format. You need every file needs a unique ID, which is available in the container. So you run Captain Proto ID, and it will give you every time another unique ID or random ID. And we define here one struct objects, which has one key, and using an unsigned integer of 16-bit. For the next node, the metadata node, we also will need a struct. For that one we have 4 keys, category, vehicle, driver, issue, which will all be type text. You can rename keys, can rearrange them. The important part is that the index after the add stays the same, and you can add additional fields. It will be backward compatible with the format on disk. In order to use the node, we need to define it in the configuration. So for one, the node is listed here in the section nodes, our objects node, and the next one also the metadata node. And we added the objects node here as the final filter on the top right side, rightmost side. And we added a listing column. This is this one. And we added a listing summary. And those three, they are all pretty similar. What is written here, so the ID is important if you communicate with MARV via API. This is going to be displayed in the web interface. We want these operators to be available. We're dealing with an integer, and it is read from the objects node, the cars field of its output. The listing column works quite similar. There's no operator needed. And the summary operates on the rows, so on the rows of the listing. So what we're saying here, we want from the rows the cars field, and if one is not set, we want it to default to 0. That's if the node hasn't been run. This field is not yet available. And we default to 0, and we want to assume all of them up. Great, let's take a look. Let's set up the container with the new code. We synchronized version 3 onto it. That was the code we were just looking at together. Now, as we change the configuration, we need to reinitialize we need to tell MARV to reinitialize its database based on the new configuration. In case of the container, this is achieved by setting MARV init as environment variable. We run the container using site again, scan root detach it. We follow it on the Docker logs. This run container script will just kill any container running before. And initialized from, so it reinitialized the datasets based on the new configuration. Now we can enter the container and run our newly defined node. Can look over there. It's not sufficient to, we need to reload again to see also the new configuration. There is the rightmost cars column and the cars filter. We're selecting only one node, and there is a bug. In order to debug this, we can provide PDB. So we're instructing MARV that we want to be in there, and you see, there is obviously a bug in the code. Let's fix this. In the site folder, code, MARV tutorials, the metadata node. We need to remove this here. And let's go back to the README. Now the bug is fixed, and we can simply rerun our node. Now the node ran successfully, and when we're reloading over here, the car column is filled, the car summary view is existing, summary field is there, and we can filter for cars. So we only want bags with less than 5 cars, and there's only one left. We're setting these filters. Let's take a brief look at our other node. That's the metadata node. It's very similar to the objects node, just we use a different output type. And we're looking for the dataset YAML file. We're just using YAML to load it. And we're pushing it as dictionary because its content fits directly our metadata type, Captain Prototype. Let's take a look at the configuration for this node. For the listing column, we want to display a column with the vehicle name, a column with the driver name, and one more complex one. We want to render a link to GitLab, to the GitLab issue being tracked there. Link receives as its first argument the URL, which is metadata's issue field. And the second parameter, we can give it the title to be displayed. The title to be displayed, we just want to have the issue number to be written there. And for that, we are using the metadata issue, the URL that is. We are splitting it from the right by dashes one time, and then we are taking the item with index 1, so the second item in that list. For the filter, we also want to have vehicle and driver to be available as filters. As the metadata vehicle is a string and the driver is a string, but the subset filter, we want to be able to say, I want to filter for any data set that has any of the drivers I specified here. So we need the subset value type for that. And this expects a list. So we need to create a list here with one element, which is the driver. Having defined these in the config as well, we can run the metadata node. And should see in the moment also the fields here for vehicle, driver, and issue being filled. So we have the vehicle name, we have the drivers here, and we have the links to the GitLab tracker where the test drives are tracked. For filtering, we can use the vehicle filter. So we want all that was either TrueBotix or Falbala. And we find those two bags where those vehicles were used. That was session 3. Thanks a lot for listening. Let's go back to session 4. In the previous session, we used a custom node to read the dataset YAML file and the tracklet XML file provided by Kitty. Now in this session 4, we want to open the bag actually and extract one video stream and render a video from that. To achieve that, we're going to compose multiple nodes in a MapReduce approach. And finally, we're going to see a video as we have seen in the session 1 that was with MARV's default configuration. We're going to re-implement all of that and go through the steps. Let's start with the code again. First, we need to have an image source. The nodes before were stored in a store and had an object, had a output type. These nodes will be volatile. They will only be instantiated while MARV is running nodes for their output to be used by other nodes, but the output will not be stored. This first node uses as input ROS messages. It selects one topic from it's up here, from MARV Robotics bag messages. It looks for one topic. As you see, we built in here a small bug. This topic doesn't exist. We'll see that in a moment. We're dealing with ROS messages, so we ask for a deserialize function, which will transparently deserialize ROS1 and ROS2 messages. And as we will see shortly, if the topic doesn't exist, this deserialize function, the stream will be an empty stream, and that deserialize function will also abort the execution, so we don't need to take any further care. We know after we have a deserialize function, the topic exists, and the function will be able to deserialize the messages, be it ROS1 or ROS2. We have a bug in here, and then we have an endless loop. And in that endless loop, we are pulling the input stream until the input stream is empty. If you remember in session 3 we had only data set which was a stream of one message. Here we're pulling all messages of that stream contained in the back file. And for every input message that exists, we're going to deserialize it and publish its deserialized equivalent. So we are mapping raw serialized ROS messages to deserialized ones. The next node uses this stream of deserialized messages as its input. Same pattern, it's pulling, and then it uses one of MARV ROS image tools function to convert to an OpenCV image. In case there is an error, we assume this topic, it doesn't make sense to be processed, and we are also raising abort. Otherwise, we are pushing one OpenCV image per message, per ROS message that we have in the input stream. This is our source of images. Now we want to render a video with that. For that, we have a node which the video needs to be written somewhere, so we are persisting something in the store and we're using the file type. It's using that image stream of OpenCV2 messages as its input. We are assuming here a constant frame rate and are not calculating it, but just hard coding it. And then we have the same pattern. We are pulling our input stream until there is no messages anymore. And in the beginning there we don't have an encoder yet, so we are instructing MARV to create a file. We want to call it camera webm, and MARV will respond by having created a file and giving us a file object here. We use the shape of the first image we found in the stream to initialize FFmpeg to encode a video. And then we instruct using popen, we create a subprocess, and we're going to communicate with it through standard in. This is happening only through the first iteration of this loop, and then we are simply writing our images to the FFmpeg. So this node will reduce a stream of many messages into an individual file, a WebM container containing a video. Now, if this node actually ran, we didn't deal with an empty stream. There was actually messages, so we had an encoder initialized. We are closing standard in that will trigger signal to FFmpeg that it should stop working. We're waiting for it to be finished, and then we're publishing the video. For this video to be visible actually in a detail section, we need to render a section. For this we have a MARV node declaring the type section. We have the input, that's the video sync, and we are having a parameter in this case, title, which is defaulting to video. We are pulling the one video file. If there is no video file, there will not be any video section. And if there is a video file, we are rendering here a section. We define that up here. The section has a list of widgets, which is only one, which has the type video, and as source the video file relative path. Having defined this, we can run the nodes, exiting the old container. I'm rsyncing the code of site 4 onto the site. Wait, something is missing. We need to do configuration. Configuration. We have two more nodes that have to be persisted in the store. That is our video sync and the video section. And we want the video section to be displayed as a detail section. Now we have synced the site. We're going to MARV init again, the site folder, because we changed configuration. MARV is up and running. And we can enter the container and run the video node, the video section. It will automatically pull in all nodes it needs for it. No such option, -n, here it's 2 dashes. Okay, let's have a look. That was very quick. We go in here and there is no video section, which is strange because we are sure that this topic exists. Let's go back to the code. That was video part. No, it's the image source actually. And in the image source we had that topic which didn't exist. So the topic did not exist, the whole machinery was running, and in the end there was no section because the topic doesn't exist. Let's add this here. And you see we didn't reach the fix me code, this bug, because the topic did not exist. So this we aborted already in the make deserialize. Now after having done that, the topic exists. We need to extract MARV to rerun, because if I'm just running it now again, it will claim there's nothing to be done because it doesn't know that I changed code. So we need to tell it to please run again, and we changed code. We want the video sync to actually run again because that's the one creating the video. So we want the video sync to force that, and we could also select node the video section here. But we also can simply just say force dependent, which means the video sync will run. Anyway, all volatile nodes, the video sync needs as input. And with force dependent, also all nodes coming afterwards, which in our case is now the video section. This was still very quick. It was too quick. This is the case because I fixed the code in side 4 and we are operating on site. Here we still have that one. I'm forcing again. Now we reached the broken code. As shown before, we could debug it like this. In PDB++ and can investigate code here. For example, we can take a look at stream and we can see that this stream has a topic. And after investigating, we are fixing the code and we are running again. So this time the FFmpeg encoder should be started, which will take a little bit, and once the first one is finished, we should see output. The first one is finished. Just need to, which one is it? This one. So here we have a video section displaying a video of the test drive. This was session 4. Thank you very much, and let's head to session 5. In session 5 we want now to use Tensorflow to detect objects in that video stream and want to mark them in the video. To that end we have we need some dependencies, so we will create a custom Docker image extending onto the image being used, or the default image of MARV. Let's take a look. So Docker build is doing 2 big downloads. They will be stored in this Docker directory, which is the Tensorflow wheel, and there is a pre-trained model. And then it's instructing MARV to use the custom MARV robotics image as its name, and it's building the Docker file, tagging it as custom MARV robotics. If you look at the Docker file, it's building on the TERNARIS MARV robotics image and then installing in there TensorFlow and the pre-trained model. You probably have run that command already in the intro as a prerequisite. I'm still in the old container from session 4. I'm quitting that container, running docker build. This will send all the data in the Docker directory to the build daemon, which will take a moment. And as we did that before already, there was nothing changing. There was nothing changed. Now we take a look. What are we doing with that Docker container? We have a bounding box function in utils, which we're not going into detail at this within the scope of this session, but we have functions made available that create a detect function. We're providing it. The Docker container contains this now, the pre-trained model and the label map. And using these, we have a very simple node which uses the image source, that is the deserialized messages, as its input stream. It pulls that input stream until there's nothing there anymore, and it runs TensorFlow on each of these images and publishes then the image with visualizations. So this is a mapping function again. It's volatile. Its output is not directly being stored, and we need to make use of this function somewhere. For that, we're going to our video sync, and up here we changed. Before we had this one here as the default input stream, and now we're handing it our bbox node as default stream. So the whole setup, video sync, video section stays the same. We just plugged the bounding box in between image source and video sync. Having done this, we need to use this code. So I'm syncing site 5 onto site. We did not change configuration, so the MARV init is not strictly necessary. But it also doesn't hurt. Now take a look at the Docker logs. There should be some TensorFlow going on. No module named TensorFlow. What might be the case? We are using the wrong image. Yes. Though I was under the impression that this docker build command should have handled that for us. I found a bug in the tutorial, which of course we're going to be fixing until you have this code. Let's do this right away. We need, of course, here a redirection. Like this. I'm doing the same here. Custom MARV robotics. No, not here. It's just MARV robotics image name, and we restart the container. So MARV is up and running. We can enter the container, and as we change the wiring for the video sync, we have to force that again. marv_run bags node video sync force dependent. MARV is starting, Tensorflow is in action, and on this laptop this is going to take a while, so we'll be back in a moment. Welcome back. MARV finished running Tensorflow on the first back, and after reloading the detail view, we can look on the video section, and as you can see now, let's go to full screen, we have the detections from the TensorFlow network. This was session 5. Thank you very much for following. Let's do a quick wrap up. We showed you in these sessions how to install the MARV Community Edition, what the default configuration shipped with the Community Edition does to some example ROS1 and ROS2 bags. We implemented a custom scanner to add additional files. We used metadata from these files to display in the listing and summary views. We used the map and reduce approach for an image stream from a bag file to create a video. And finally, we used TensorFlow to detect and mark objects in that video. I hope you enjoyed it. If you want to use it in production, please take a look at the deploy section in documentation. You should put an Nginx in front of it for performance and security reasons. And please star and focus on GitLab and give us your feedback. Thank you very much. See you then.